Hello viewers. In this chapter, we are going to discuss the mathematical equations governing motion in a plane. We will see the expression for position vector, displacement vector, velocity and acceleration in motion confined in a plane. We will also discuss how motion in a plane can be described using a combination of two one-dimensional motion. Using these concepts, we then analyze projectile motion and circular motion. In one-dimensional motion, the object moves in a straight line. Therefore, only one physical parameter along with time is sufficient to specify the position of the object at any instant. In the case of two-dimensional motion, the object moves in a plane. Consequently, we require two physical parameters to specify the position of an object in the plane at any instant. When a particle moves in a plane and its path is not straight line, then we need at least two coordinate axes to describe its motion, and such type of motion is two-dimensional motion or motion in a plane. To study two-dimensional motion, we need to know about various quantities. Let us start with the position vector. The position vector is defined to describe the position of any point at any particular time. It is a vector drawn from the origin towards the point of interest. If position coordinate of point P are known to be x and y, then the position vector of the point can be written as r equal to xi cap plus yj cap. Here I cap and j cap are the unit vectors along the x and y axis respectively. Next, we have displacement vector. The displacement vector is a vector that gives information about the change in the position vector of a particle in motion during an interval of time. Suppose a particle is at point P with position vector r1 and after some time it moves to a new position Q with position vector r2. The difference between two position vectors r2 and r1 denotes the displacement vector. The magnitude of the displacement vector is the shortest distance between the initial point and the final point of the particle in motion for a given time interval. Its direction is taken from the initial point towards the final point. We can also resolve the displacement vector into its x and y components. We all know velocity is the rate of change of displacement with respect to time. In this way, we are actually calculating the average velocity in a time interval. The direction of average velocity in a time interval is the same as that of the displacement vector itself. If we start reducing the time interval of our measurement, then for an infinitesimally small time interval, we get instantaneous velocity, where its magnitude and direction are expressed in this way. Next, we have acceleration, which is defined as the rate of change of velocity with respect to time. If the total rate of change of velocity is divided by the time interval, then it is termed as average acceleration. Using the concepts of a very small time interval, we can evaluate instantaneous acceleration, which is the limiting value of average acceleration when time interval for the calculation approaches 0. Instantaneous acceleration can also be resolved along the x and y axis. The direction of acceleration is along the direction of change in velocity. From the concepts of mechanics, we know acceleration can be defined as the force per unit mass. Using the concept, we can say that direction of acceleration is along the direction of the net force. The analysis of motion in a plane can be simplified by considering it as two separate problems of one-dimensional motion in a perpendicular direction. Time is the common link between these two one-dimensional motions. Let there be a particle moving with constant acceleration in a plane and its acceleration is given by a. At time t equal to 0, the velocity of the particle is u, and at time t equal to t, the velocity of the particle becomes v. The first equation of kinematics in vector form can be written as v equal to u plus at. We can rewrite the expression in component form along the x and y axis. This shows the first equation of kinematics can be written using two equations which are independent along x and y axis separately. Similarly, we can express s equal to ut plus half at square and v square equal to u square plus 2as into two independent equations along x and y axis. Now let us discuss the projectile motion. When an object moves under gravity near the surface of the earth, then the acceleration acting on the object remains constant. This kind of motion is termed projectile motion. Here we assume that throughout the movement the acceleration due to gravity doesn't change and air resistance on the object is zero. In this example of projectile motion, an object is thrown at a particular angle theta with an initial velocity u. So the information we are having here is initial velocity, angle of projection, acceleration along the vertical direction which is minus g, and acceleration along the horizontal direction which is 0. In this problem, we have to calculate the following things: instantaneous velocity, maximum height of the projectile, time of flight, the range of the projectile, finally the equation of the trajectory. To calculate the instantaneous velocity, we need to evaluate the x and y component of velocity at any instant. Here, the initial velocity along x-axis is u cos theta and along y-axis is u sin theta. Putting these values, we can evaluate the magnitude and direction of instantaneous velocity. When we throw a projectile, it attains a maximum height and then it falls down. Using the velocity displacement relation along y-axis, we can evaluate the maximum height an object can attain. The time of flight is the time taken by the projectile to complete its journey. From the trajectory, we can notice that the displacement along y-axis is 0 at the starting point and again it becomes 0 when the projectile completes its trajectory. So, using the displacement acceleration relation along the y-axis, we can evaluate the time of flight. Range is defined as the maximum distance a projectile can reach from its point of projection. If we multiply the time of flight and horizontal component of velocity, we can get the expression for range. From simple mathematical tricks, we can see for a fixed initial velocity of projection, range becomes maximum when the angle of projection becomes 45 degree. For the expression of equation of trajectory, we have to eliminate time from displacement equation along the x and y axis. This can be done by calculating the value of t from the displacement equation along the x axis and then putting the value of t into the displacement equation along the y axis. Another type of projectile is horizontal projectile. In this case, the object is thrown horizontally with some velocity from a height. Again, in this case, the acceleration along x-axis is 0 and along y-axis it is g. Here, g is positive because the direction of displacement along y-axis and the acceleration acting on the object is in the same direction. In this case, we have to find the expression for equation of trajectory, time of flight, range of projection, and instantaneous velocity. The equation of trajectory can be evaluated again by eliminating time from displacement equations along the x and y axis. This can be done by calculating the value of t from the displacement equation along x axis and then putting the value of t into the displacement equation along y axis. The time of flight can be calculated from s equal to ut plus half at square equation. Here we know the height from which the projectile is thrown and that is the displacement along y direction. Putting the values of other quantities along y-axis, we can get the expression for time. As the acceleration along x-axis is 0, we can evaluate the range using horizontal component of velocity and time of flight. For the evaluation of instantaneous velocity, we have to evaluate the velocity components at any instant and then using the velocity components, we have to evaluate the expression for its magnitude and direction at the same time. At next, we have circular motion. When an object moves in a circular path, it is said to have circular motion. The circular motion differs from linear motion in one very important aspect. In circular motion, the direction of motion is changing continuously. Hence, any object exhibiting circular motion always exhibit some kind of acceleration. Here, in the diagram, we can see one object moving in a circular path is at point P1 at time t1. and after some time t2 it moved to point P2. The corresponding angles are theta 1 and theta 2. The physical quantities associated to circular motion are angular displacement, angular velocity, angular acceleration, time period, and frequency. The expressions for the above mentioned physical quantities are shown here. Parameters for the linear motion and circular motion can be related using the following relations. We have already mentioned that when an object undergoes circular motion in a plane, it undergoes acceleration. To obtain a quantitative expression for acceleration, let us consider the velocity of the particle at point A is represented by Va and at point B is represented by Vb. The time interval it took to reach from point A to point B is delta t, and the arc AB is making an angle delta theta at the origin. We can form the velocity vector diagram from the above diagram, and if we consider the time interval to be infinitesimally small, then the vector Va and Vb becomes nearly parallel to each other, and the vector representing the change in velocity becomes perpendicular to both Va and Vb. Hence, the direction of acceleration named centripetal acceleration is towards the center of the circular path. Its magnitude can also be derived from the diagram, and its instantaneous value is v square by r. In this chapter, we have discussed the mathematical equations governing motion in a plane. We have also discussed projectile motion and circular motion.